Good evening. My name is Hunter, and this is Content Review for Chemistry 221 students. I understand you have an exam coming up, so this is a good opportunity to do some practice problems that may reflect questions on your exam. We're going to be going over electron configurations, a little bit more an added layer of complexity on what we did last week, and take a look at some more periodic trends. These are things that continue to help me in my chemistry education. I am the, these are tools that I keep falling back on. So they are or keep coming back to. They are good things to review and to know and to understand about the periodic table that will enhance its utility to you in as you continue your chemistry education. So without any further ado, um, when we get to question 80, I will go over this a little bit more in detail, but the term isoelectric just means, so prefix iso, meaning same, and electric, we're talking about electrons. So same electrons, the same number of electrons. That is all that this word means. That will make more sense when we get to this next question. And I think that's all I got. Let's jump into it. There we go. First question. So which atom has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d7, and 4s2? Now you might be inclined to look at this last one here. This is usually the shortcut that I would recommend, is you look at the last set of the last electron orbital. You look at 4s2. That tells you that you're in group 4. Group 4, S. S is these two columns, or sorry, period 4. Group 2, and that would give you calcium. It's not calcium. I'm going to make sure you can see this. So remember this flow here. The way that this electron configuration is written in the problem is incorrect. We would normally go 1s2, 2s2, 2p6, 3s2, 3p6. We would not go straight into 3D. We would go to 4s2 first, and then back to 3d7. Let me say that again. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d7. So 3d, what was it? Yes, 3d7. 1, 2, 3, 4, 5, 6, 7. Sorry. Gives us cobalt. So cobalt is the identity of this particular electron configuration. And that is because this electron configuration is misleading. So be very, very careful of that. You would get this wrong on an exam if you wrote it this way, I am pretty sure. But assuming it's written correctly, you can usually look at the last figure in that electron configuration and use that as a shortcut, because 4s2 would get you to group 4, and the second to the right, yeah, second over in the s orbital would give you calcium. Okay. Number 62. In one area of Australia, the cattle did not thrive despite the presence of suitable forage. An investigation showed the cause to be the absence of sufficient cobalt in the soil. So there's an insufficiency of cobalt. Cobalt forms cations, so positive charge, in two oxidation states, cobalt 2 plus and cobalt 3 plus. Write the electron structure of the two cations. Well, how nice of them to have already written, if incorrectly, the electron configuration of cobalt in its ground state. So let's go ahead and just copy that over, 1s2, 2s2, 2p6, 6, 3s2, 3p6, and I'm slowing down because I want to make sure I get this right, 4s2, 3d7. So that's cobalt in its ground state. If we have a cation with a 2 positive charge, that we have to shed charge somehow, so we're going to shed 2 of those electrons. And so everything would be the same up to 3d. 7 minus 2 is 5. So 3d5, and that would be our cobalt 2 positive cation. And for cobalt 3 positive, it would be the same deal with 1 less electron again. That's really it really is that simple. Check something here really quick. Yes. Second guessing myself now, but no, I'm pretty sure that is correct. Okay. Periodic variations in element properties. So based on their position in the periodic table, predict which has the largest atomic radius. We have lithium, rubidium, nitrogen, fluorine, and iodine. I'm going to share with you my favorite, again, I've shown you this before, but I'm going to show you some new functionality with this. This is ptable.com. And what I want to show you here, in its default, the way that it loads, it's color coding based on series. What you can do here is with this section at the top, I want to make sure you can see my mouse scrolling, and it looks like you can. You can select, let's try electronegativity. When I click on electronegativity, it creates a color gradient on your periodic table, and it very conveniently gives you a key for what that gradient means. So more blue colors means minimal electronegativity, and more yellow means maximum electronegativity. And you will notice that in the bottom left corner of your periodic table is that true primary blue. That is your least electronegative atom. And our most electronegative atom, or species, is fluorine up here in the extreme top right. Now, what does this have to do with atomic radius? Well, actually quite a lot. But you can also, if you want to just kind of, I don't know, visualize this a different way, you can click on atomic radius and you will notice a similar trend. Again, looking at our key, so the most teal would be maximal. This is maximum radius down here at the bottom left. And smallest radius, top right. So the general trend here is as we go up and right on the periodic table. If you look at me, it might be backwards. So look at the table. If you start in the bottom left and go up and to the right, your atomic radius will tend to get larger. So now, having that information, let's go back to the prompt here. Based on the positions on the periodic table, predict which has the largest atomic radius. All right, I'm pulling up the questions on multiple screens so that I can possibly, there we go, keep track of what we're looking for. So we're going to scroll up here, and I'm going to highlight in We'll try red and see if that works. We're looking for lithium. We're looking for rubidium, nitrogen, fluorine, and iodine. So remember we said that atomic radius, I'm going to do radius, increases as we go up and to the right. So max atomic radius. So that tells us right away that our largest one, our largest species is going to be fluorine, followed by nitrogen's pretty close, would be a good educated guess. Maybe lithium, right? And then going down, rubidium and iodine are in the same period. And so I'm going to go ahead and say that iodine probably has, uh, excuse me, minimum radius. We're getting smaller as we go up and to the right because we have increasing electronegativity. So I was doing this in terms of electronegativity because oh, you can't even see this because I'm putting it behind my head. That's fine. No mistakes were made whatsoever. I was sorting these by electronegativity, uh, which would be the exact opposite trend of atomic radius. So fluorine was our smallest radius, followed by nitrogen, followed by lithium, followed by iodine, and rubidium. Rubidium would be our largest, our greatest radius. I'm going to put that answer where it belongs. Paste. Okay. So don't be like me. Understand that these trends are connected. These traits, electronegativity and radius, are connected, but that they have opposite trends in terms of, I guess, scale. All right, so based on their positions on the periodic table, rank the following atoms in order of increasing first ionization energy. So the energy required to get that, to achieve that first ionization state. And forgive me, I don't know if that means gaining or losing an electron, but that, again, I'm going to keep using, um, now where did you go? I'm going to keep using ptable.com because it just visualizes these so very nicely. So we're doing ionization energy. You can click on it and it'll give you that scale again. So maximum ionization energy is way up here at helium, and lowest again is in bottom left. You will notice that there are some exceptions in the middle of the table here. These are nice trends. They are useful at making educated guesses, but there are obviously going to be exceptions throughout these. So first ionization energy, and actually first ionization energy is going to be informed a lot more uh, by orbital shape than something like electronegativity because of the distribution of electrons, I believe. So I'm gonna hedge that a little bit but I think that is the reason for these exceptions that you're seeing in the middle of the periodic table. All right, so going back to here. Based on the position of the periodic table, rank the following atoms in order of first ionization energy. We've got magnesium, oxygen, silicon, sulfur, and silicon. We've got lithium. We'll try blue this time. Lithium, magnesium. What was it? Oxygen, oxygen, and sulfur and silicon. All right. Magnesium, oxygen, sulfur, silicon. I've included one that we don't need. Yeah. Magnesium, oxygen, sulfur, silicon. Okay, magnesium, oxygen, sulfur, and silicon. Okay, and now we're looking at, generally, ionization energy. Max. Now let me let me check that again. Yes, it looks like max is in the it increases as we go top right, up and to the right. So min. Cool. Okay, so based on that, oxygen and sulfur are in pretty close proximity here. I feel comfortable saying that oxygen is our leader, followed by sulfur, followed by silicon, and then magnesium. So oxygen requires the most energy to ionize. Ionization energy may also be informed by electronegativity. Um, Electronegativity is something that you will just keep coming back to because it affects so many other properties of atoms. I remember this being really, really key to my ability to make it through organic chemistry. So if you're continuing on in your chemistry education, um, finding different ways of conceptualizing this is important. But electronegativity is the one that kind of grounds my understanding of this. Um, Oxygen is the most electronegative, means it wants to hold its electrons the most. That also tends to mean that it pulls those electrons closer into the nucleus than these other atoms. And so this, you would see a similar trend, rather an opposite trend with atomic radius. So oxygen would be your smaller atom compared to sulfur, silicon, and then magnesium. So same kind of trend, and it all kind of comes back to this same characteristic in my mind. All right, so atoms of which group in the periodic table have a valence shell electron configuration of ns2? So n is just any number, and s2 is the s is the orbital, and 2 is the number. So remember, so we're looking at groups. These are columns. So groups 1 and 2 we know is our s orbital, the only exception being helium up here at the top right. Let me get rid of some of this visual clutter here. So S2 would be anything, I'll stick with blue, anything in this second column here. So beryllium, magnesium, calcium, strontium, barium. Oop. Any atom in group 2 will have a valence shell electron configuration of ns2. List the following ions in order of increasing radius. So now we've added a layer of complexity. We know that periodic trend when we're looking at elements in their ground state, but now we're looking at these species ionized. So we have added or removed electrons. And this is going to produce some different behaviors than we have seen previously. Okay. So back to our periodic table. We're going to stick with red because that was working well. We've got magnesium, and it's a 2 plus. We've got lithium. Lithium, where are you? Right next to it with a plus charge. We've got bromine with a negative charge. And we have tellurium with a 2 negative charge. Okay, so what do these charges mean? If it's a cation, we have lost an electron. That means we're going to have a smaller electron configuration. And if we have a negative charge, we have added an electron, and that is going to move that electron configuration forward. What do I mean by that? So looking at lithium up here, we have a positive charge. That means that our electron configuration is going to go back and around to the electron configuration of helium. Okay, so 1s2 is that lithium cation electron configuration. Same thing for magnesium. We're going to go back two spaces basically. So we go from magnesium to sodium on back to neon. For bromine, we have a negative charge, anion, so we're moving that forward. That's going to jump over here to krypton. And for tellurium, we do two of those, xenon. So it'll have the same electron configuration as xenon. Okay, so what does this mean for our atomic radius? Same trends apply, but we're just holding these different electron configurations in consideration. So I'm going to be perfectly honest. I don't understand this as well. I don't know which one holds priority, and I'm sure there's a rule for this that we could, actually, there's probably a rule for this that we could look up. So I'm going to do that with you guys. So I'm going to refer to the textbook. Let's do show me table of contents. We're in chapter 6, periodic variations in elemental properties, electron structure. Okay. Show me so I'm in 6.5, periodic variations in elemental properties. I want to make sure I explain this correctly for you, and this is good review for me as well. So, no, I don't think that's it either. Hmm. Variations in ionic radii. Ionic radius is the measure used to describe the size of an ion. Yes. Cations. A cation will always have fewer electrons and the same number of protons as the parent atom and is smaller than the atom from which it is derived. Okay. Okay, so that's our answer. It's always going to be smaller from the atom from which it was derived, and because it has more protons, it has a greater electro. It has a greater difference in charge between the electrons that remain and the protons in the nucleus. So that is going to be part of it. As electrons are removed from the outer valence shell, the remaining core electrons occupy smaller shells, experience a greater effective nuclear charge, and are drawn even closer to the nucleus. Yep. Cations with larger charges are smaller than cations with smaller charges. Okay, so that is why magnesium and lithium are fairly close here, but the difference in charge, I think, yes, the difference in charge is going to establish our magnesium cation as having a smaller atomic radius than our lithium cation. Yeah. By contrast, an anion, or a negative ion, is formed by the addition of one or more electrons to the valence shell of an atom. This results in greater repulsion among the electrons and decreases in the Oh, they're using an abbreviation here that I don't remember. Effective nuclear charge. Decrease in effective nuclear charge per electron. Both effects, the increased number of electrons and the decreased effective nuclear charge, cause the radius of an anion to be larger than that of a parent atom. For consecutive elements proceeding down any group, okay, proceeding down any group, anions have larger principal quantum numbers and thus larger radii. Okay, so in that case, bromine, with our singular negative charge, would be smaller than tellurium. Yes. Yes. Okay. There you have it. So losing electrons has a much greater difference. Losing multiple electrons has a greater effect on nuclear radius for atoms that are close to each other in the periodic table, which is why magnesium, even though it's lower down in the group, would be smaller than lithium, than the lithium cation. There you have it. Okay. How are we doing on time? We're doing awesome. We're almost done, folks. So which of the following atoms and ions is or are isoelectronic? That just means same number of electrons with a sulfur 2 plus cation. A sulfur 2 plus cation. Let's clear my board here. Sulfur 2 plus. So 2 plus means we've lost 2 electrons, which means we're actually looking at something with the same ground state as silicon. Okay, and that would be 1s, 2s, 3s, 2, 3p2. Yeah, so we're looking at anything that is isoelectric and would end with an electron configuration of 3p2. Let's have a look. A silicon cation couldn't be it because we wouldn't have the same in that ground state. So a ground state silicon would, but not the silicon 4 plus cation. Let's look at chlorine 3 plus. Chlorine 3 plus. 1, 2, 3. Chlorine 3 plus would be isoelectronic. Yes. Let's look at argon. Probably not, because argon is in its ground state, right? Actually, yes. So if it were a sulfur 2 minus anion, that would be true. As I think is arsenic. Yes, it is. And it was 3 plus. So arsenic, 1, 2, 3. Probably not. Silicon we already established was the ground state that it was isoelectronic with. And aluminum 3 plus. Let's take a look. We have aluminum. Give up 3 electrons. 1, 2 would give us neon, so no. So chlorine, 3 plus cation, and silicon in its ground state were, of the options available, were isoelectronic with sulfur 2 plus cation. All right, last one, I think. Yep. The ionic radii of the ions sulfur 2 minus, chlorine minus, and potassium plus are 184, 181, and 138 pico, I think that's picometers, respectively. Pico is 10 to the negative, not, what is it? Ten to the negative 12. Explain why these ions have different sizes even though they contain the same number of electrons. So they're all isoelectronic with each other. Same number of, let's see, same number of electrons. Why do they have different radiuses? We kind of touched on this already, right? So sulfur, chlorine, and potassium plus. Sulfur, chlorine, and potassium. Excuse me. Is that right? Yes. Okay. So they all have an electron configuration, that of argon. Okay. So the question is, why do they have different radii? Well, remember we touched on the fact that because you have we're starting with different numbers of protons and neutrons in the nucleus of each of these species. And those are going to have greater or lesser impacts on the remaining electrons in the new ionized electron configuration. So for sulfur, we've added electrons. And let's go back. Sulfur was our greatest, yes. So we've added electrons. Those electrons take up more space, first of all. They also repel each other more. Um, and so they don't want to be close together, and they also need more space, need to occupy more space. They're more energetic. And that is why those two additional electrons contribute a great deal to the atomic radius. Same thing for chlorine, to a lesser degree because it's just the one added electron. Um, and it's also to a lesser degree because we have more protons and neutrons to begin with to pull on those electrons. So that is slightly smaller again, even though it has the same electron configuration as that sulfur anion. Looking at the potassium cation, we've lost an electron, right? We're giving up space, right? It doesn't need as much space to occupy. We're giving up charge, and giving up that negative charge means that the remaining electrons are repelling each other less, and the nucleus, that positively charged nucleus, can exert greater pull on the remaining electrons. So explain why these ions have different sizes, even though they contain the same number of electrons. Um, number of protons. Let's see. I'm sure there's a tidy way of. That was a very long-winded way of explaining it, and I want to make sure that um, this is both accurate and precise and concise. I want to keep it short if I can. How would I? Hmm. let's see how the textbook. Well, we already read the textbook's explanation of this. So increasing the number of electrons requires more space, and the electrons repel each other and are pulled less tightly by the nucleus. Nucleus exerts less pull. How do I want to say that? Increasing the number of electrons takes more space, and the electrons repel each other, and nucleus exerts less attractive force on those electrons. Giving up electrons requires less space, and the nucleus exerts greater relative force of attraction on the remaining electrons. I want to make sure I'm not missing anything here. Yeah. I'm sure my explanation is incomplete, but these are the aspects that I am sure of, right? Let's read the question one more time to make sure we totally got this. The ionic radii of the ions, sulfur 2 negative, chlorine negative, potassium positive. Explain why these ions. Explain why these ions have different sizes even though they contain the same number of electrons. Yeah, I think it mostly has to do with the number of protons and neutrons that are specific, that determine the identity of those different species, and acquiring or getting rid of electrons changes that relative difference in charge and the forces of attraction between the nucleus and the electrons, and also between electrons. Yeah, I'm satisfied with that explanation. Hopefully your professor would be as well. And that's all I have for you today. Feel free to email me with questions if you're watching, if you're watching the recording on YouTube. I hope you found this helpful. Um, good luck on your exams all. Rest well. I'll see you next week.